Damascus Steel. In the early 12th century, somewhere between the markets of Damascus and the furnace towns of the Near East, European crusaders encountered a blade that did not behave like ordinary steel. It was dark, fluid, and strangely alive under sunlight. Across the surface ran rippling bands that looked like flowing water trapped inside metal. When merchants drew the sword from its sheath, the edge seemed impossibly thin, yet the blade did not shatter. It could bend slightly, return to shape, and hold a cutting edge through repeated use. To men accustomed to iron that chipped, dulled, or cracked under pressure, this was not just a weapon. It was a material that appeared to disobey the rules of metallurgy. The blade would later be known as Damascus Steel. The name did not describe one single workshop, but a legendary class of crucible steel weapons traded through Damascus and forged from high-carbon ingots often associated with Wootz steel from India and Central Asia. These blades were recognized by their watery pattern, a surface of silver and black waves running through the metal like smoke beneath ice. The pattern was not painted, it was not engraved, it emerged from the internal structure of the steel itself, formed through carbon, heat, impurities, and forging methods that required extreme control. A true Damascus blade was not simply hard. Hard metal can become brittle. Soft metal can survive impact, but lose its edge. Damascus steel appeared to balance both. Microscopic studies of surviving examples have shown complex carbide structures within the metal, including bands that helped create the famous pattern. Ancient smiths did not have modern microscopes, electric furnaces, or digital temperature probes. Yet somehow, through sight, sound, color, and inherited technique, the smiths controlled a process that modern researchers still struggle to reproduce exactly as the old masters did. The secret may have begun before the blade even reached the forge. Some historians believe the original material depended on specific ore deposits containing trace elements such as vanadium, tungsten, or other impurities. These elements may have encouraged the formation of the internal bands during heating and hammering. If the ore changed, the steel changed. If the temperature rose too high, the pattern vanished. If the blade was hammered too aggressively, the structure collapsed. The entire formula lived inside a narrow corridor of conditions. One wrong step, and the legendary material became ordinary steel. Then the corridor closed. By the 18th century, the great Damascus blades had largely disappeared from production. Trade routes shifted. Old mines were exhausted or abandoned. The crucible ingots stopped arriving in the same form. Families of smiths died without writing down every stage of the process. Workshops that once guarded their methods like sacred inheritance were swallowed by war, empire, and industrial change. By the time European metallurgists tried to understand the blades scientifically, they were already studying relics, not a living craft. Attempts to recreate Damascus steel have produced beautiful pattern-welded blades and modern crucible steels, but the exact historical process remains disputed. Some modern smiths can imitate the look. Some can approach the chemistry. Some can create excellent blades. But the old material, the one whose pattern rose naturally from the steel's hidden structure, remains a moving target. The mystery is not whether ancient smiths were skilled. The mystery is how a technology so valuable could vanish without a complete technical record. And that is what makes Damascus steel so unsettling. This was not a decorative luxury. This was a battlefield material, a symbol of status, survival, and fear. A soldier who held such a blade held more than metal. He held generations of invisible knowledge, mined from forgotten earth, refined in sealed crucibles, and finished by hands trained to read fire like language. If the formula was lost by accident, it reveals how fragile human progress can be. If the formula was guarded until it died, it reveals something even darker. Some technologies do not disappear because they fail. They disappear because too few people are allowed to know how they work. Greek fire. In 674 CE, as Arab fleets closed around Constantinople, the Byzantine Empire appeared to be nearing collapse. The city was surrounded by water, stone, and desperation. Enemy ships pressed toward the harbor, expecting another siege decided by numbers, wood, and iron. Then, from the walls and from the decks of Byzantine vessels, strange bronze tubes were aimed toward the sea. A pressurized liquid burst outward. The surface of the water ignited. The attackers were not watching ordinary flame. The fire clung to timber. It crawled across waves. It appeared to burn even where water should have smothered every spark. Ships that tried to escape carried the blaze with them. Men who jumped into the sea found no safety beneath the foam. The weapon roared across the harbor like something pulled from beneath the earth and taught to obey an empire. Constantinople survived, and the material that helped save it became one of the most guarded secrets in military history. The Byzantines called it liquid fire, sea fire, or Roman fire. Later generations would know it as Greek fire. It was not a single flame, but a compound, a hidden mixture of combustible substances projected through siphons, sealed jars, or hand-thrown containers. Historical descriptions suggest the material could ignite violently, resist water, and spread terror out of proportion to its physical size. Some accounts describe a thick liquid that stuck to surfaces like burning glue. Others describe a chemical flame that could only be fought with sand, vinegar, or smothering agents rather than water. Modern scholars have proposed many possible ingredients: petroleum, naphtha, pine resin, sulfur, quicklime, pitch, and other volatile materials known in the Eastern Mediterranean. But no reconstruction has fully settled the question. Naphtha can burn on water. Resin can help a flame cling to wood. Sulfur can intensify combustion. Quicklime reacts violently with water and releases heat. Yet none of these explanations alone captures the full horror described in Byzantine warfare. The true power of Greek fire may have come from proportions, preparation, storage, pressure, and ignition method working together as one weapon system. That is what makes the compound so difficult to recover. Ancient formulas were rarely written like modern chemical manuals. A recipe might say to mix resin with oil, but omit the source of the resin, the temperature of distillation, the age of the petroleum, the shape of the container, the pressure inside the bronze tube, or the moment when the spark entered the stream. Greek fire may not have been only a material, it may have been a complete procedure. Without the machine, the mixture failed. Without the mixture, the machine was useless. The Byzantine state understood this danger. The formula was not shared openly among soldiers. It was protected as an imperial secret, reportedly restricted to a small circle of specialists and passed through controlled channels. The siphon operators were not merely artillery crews. They were guardians of a weapon that could decide the fate of the empire. For centuries, Greek fire appeared in moments of existential threat, then retreated again behind sealed doors and military silence. That secrecy became its own death sentence. As Byzantine power weakened, the chain of knowledge fractured. Workshops disappeared. Engineers died. Political crises consumed the capital. Crusaders sacked Constantinople in 1204, scattering treasures, manuscripts, and technical traditions. When the empire finally fell in 1453, the authentic formula for Greek fire was already lost, preserved only in chronicles and battlefield terror. Today, chemists can create substances that burn on water. Militaries have produced napalm, incendiaries, and fuel gels far more destructive than anything the Byzantines likely possessed. But Greek fire remains different because the original material was never recovered as a verified formula. The empire kept its secret so well that history inherited the fear, but not the recipe. If Greek fire was merely a clever mixture of known substances, its disappearance is still remarkable. If it required a lost chemical process, then the Byzantines held a weaponized material, science far more advanced than their enemies understood. Either way, the lesson is chilling. Some materials are not lost because they are forgotten by everyone. Some are lost because they were remembered by too few. And when the last keeper of the flame died, the sea went dark again. Flexible glass. In the 1st century CE, during the reign of Emperor Tiberius, a craftsman was said to have walked into the imperial court carrying a small drinking vessel unlike anything Rome had ever seen. The object looked like glass. It was clear, polished, and finely made, the kind of luxury item that would have belonged on the table of senators, generals, or emperors. Then the craftsman did something no one expected. He threw the vessel onto the stone floor. It did not shatter. According to the ancient story, the vessel dented like soft metal. The court froze. Glass was supposed to break. That was the nature of glass. It was beautiful because it was fragile. It was valuable because one careless movement could destroy it. But this strange cup had struck hard stone and survived. The craftsman then took a small hammer and tapped the dent back into shape, restoring the object as though the damage had never happened. If the account is even partly true, Rome had just witnessed a material that should not have existed in the ancient world. The substance became known in later retellings as flexible glass, or vitrum flexile. No surviving sample has ever been verified. No workshop has been identified. No complete technical recipe remains. The entire material exists at the edge of history, preserved through ancient literary references and repeated as a warning, a marvel, or perhaps a rumor too dangerous to ignore. But the details of the story are what make it so unsettling. The object was not described as bronze, silver, or horn. It was described as glass, transparent, elegant, yet able to deform without breaking. To understand the danger of that claim, one has to understand Roman material culture. Glassmaking was already an advanced craft in the empire. Roman artisans produced cups, bottles, windows, mosaics, and decorative vessels using furnaces capable of reaching extreme heat. They understood coloring agents, blowing techniques, molds, and surface finishing. But ordinary glass remains brittle because of its internal structure. Once stress passes a certain threshold, cracks spread rapidly through the material. A flexible glass would require either a radically different composition, an unknown treatment process, or a structure that prevented cracks from propagating. Modern materials, science has produced forms of toughened glass, flexible glass sheets, and transparent polymers, but those rely on industrial processes, precise chemistry, and manufacturing systems far beyond the known Roman toolkit. That is why the ancient account remains so provocative. If flexible glass was real, it suggests that one Roman craftsman discovered a method of modifying glass at a structural level without leaving behind any recognized technological lineage. The reaction attributed to Tiberius is even darker. Instead of rewarding the inventor, the emperor allegedly asked whether anyone else knew the secret. When the craftsman said no, the emperor had him executed. The reason given was not superstition, it was economics. A glass that did not break could reduce the value of precious metals. Gold, silver, and luxury goods depended on scarcity, fragility, and replacement. A transparent material that survived impact could disrupt an entire market of elite objects. The story may be exaggerated, it may be political satire, it may be a moral tale about rulers fearing invention. But the idea at its center feels disturbingly familiar. A material appears that could change everything. The ruler does not ask how to develop it. The ruler asks how many people know. No artifact has surfaced. No Roman furnace site has produced proof of such a composition. No glass vessel has been found that can be hammered back into shape. And yet, the legend survived because the fear behind the legend was believable. Rome knew how to absorb useful technologies. Rome also knew how to bury threats to power. If flexible glass never existed, the story still reveals an ancient anxiety about invention. If flexible glass did exist, even once, then one of the most revolutionary materials in history may have been destroyed not because it failed, but because it succeeded too well. The cup did not break. The man who made it did. Roman concrete. In 37 BCE, along the volcanic coastline of the Bay of Naples, Roman engineers began pouring a gray mixture into the sea. To any observer, the act should have looked absurd. Water destroys ordinary mortar before it can harden. Salt attacks stone, corrodes metal, and tears apart weak construction over time. Yet the Roman mixture did not dissolve. It settled beneath the waves, hardened in place, and became the foundation for harbors, piers, breakwaters, and seawalls that would stand for centuries. The material was not glamorous like gold, nor terrifying like Greek fire. It did not flash in battle or glow in temple chambers. It simply endured. That endurance may be the most disturbing thing about Roman marine concrete. Many modern concrete structures begin cracking within decades when exposed to seawater. Roman harbor concrete has survived for nearly 2,000 years, battered by tides, salt, storms, and biological growth. In some locations, the ancient material appears not merely preserved, but strengthened by the very ocean that should have consumed it. The formula relied on volcanic ash, lime, seawater, and stone aggregate. The most prized ash came from regions near Pozzuoli, where volcanic deposits created a powder later known as pozzolana. When mixed with lime and seawater, the ash triggered chemical reactions that produced a cementitious material capable of hardening underwater. Roman builders did not describe this in modern mineral language, but the results were visible in stone. Harbors rose where waves had once made construction impossible. The empire extended its control not only across roads and aqueducts, but into the sea itself. Under magnification, the ancient concrete reveals a strange internal world. Mineral crystals grow through the material like hidden veins. Seawater entering tiny cracks can react with volcanic components and form new binding phases. Instead of simply widening fractures, the ocean may help fill them. This gives the material an almost self-healing character, not alive, but reactive, not magical, but engineered through a relationship between stone, ash, lime, and salt water that modern construction abandoned for speed, uniformity, and industrial scale. The most unsettling part is that the Romans may not have understood the chemistry in theoretical terms, yet they understood the behavior. They knew which ash worked. They knew where to quarry the aggregate. They knew how to place the mixture underwater before waves tore it apart. They knew how long to let it cure, how to pack it, how to build wooden forms, and how to match materials to location. The recipe was not just ingredients. The recipe was geology, labor, timing, coastline, and craft. Then the empire fractured, trade routes collapsed, quarry knowledge vanished. Local building traditions dissolved into regional survival. The exact procedures used by Roman marine engineers stopped being copied at the same scale. Later, builders inherited the ruins, not the full system that made the ruins possible. Medieval and early modern construction moved in different directions, relying on lime mortars, stone masonry, and eventually Portland cement. By the time modern scientists began asking why Roman concrete lasted so long, the living chain of practical knowledge had been broken for more than a millennium. Today, researchers can analyze Roman concrete and identify many of its components. Some experimental mixtures attempt to replicate its durability, but recreating the material exactly is harder than copying a list of ingredients. The original ash varied by deposit. The lime may have been prepared at specific temperatures. The mixing could have left reactive fragments inside the material. The seawater chemistry, curing conditions, and aggregate selection all mattered. A modern laboratory can imitate the composition, but not easily recreate the entire ancient construction environment. That is why Roman marine concrete belongs in this archive of lost materials. It was not lost because no one could see it. It was everywhere. It was visible in harbors, walls, and ruins across the Mediterranean. But seeing a material is not the same as understanding how to make it. The sea preserved the evidence while history erased the instructions. If Rome built concrete that grew stronger in salt water, then modern progress carries an uncomfortable contradiction. We have taller buildings, faster machines, and stronger analytical tools. Yet some of our structures die young, while ancient piers still stand beneath the waves. The Romans did not conquer the sea by resisting it. They built a material that made the sea participate. Maya blue. In 1931, while researchers examined fragments from ancient Maya sites in the Yucatan, they noticed a color that should have been gone. The stone had weathered, the plaster had cracked, the temples had endured centuries of heat, rain, invasion, abandonment, and jungle growth. But the blue remained. It clung to murals, pottery, sculptures, and ritual objects with an intensity that seemed almost unnatural. The shade was neither ordinary turquoise nor simple indigo. It was deeper, colder, and strangely permanent, like a piece of sky locked inside mineral dust. This material became known as Maya blue. At first glance, it seemed like a pigment, but the more scientists studied it, the less it behaved like one. Organic dyes usually fade under sunlight. Plant-based colors break down under humidity, acid, and microbial decay. The tropical environment of Mesoamerica should have erased the color long ago. Instead, Maya blue survived for centuries with astonishing stability. Rain did not wash it away. Heat did not destroy it. Weak acids failed to strip it. Time attacked the buildings around it, but the pigment stayed behind like a signature from a vanished chemistry. The secret lay in its unusual structure. Maya artisans combined indigo, a plant-derived blue dye, with palygorskite, a fibrous clay mineral. Under heat, the organic dye appears to enter or bind within the channels of the clay, creating a hybrid material that is neither fully mineral nor fully organic. This union gave the color its extraordinary resistance. The dye gained protection. The clay gained color. Together, they formed a pigment that could outlast the civilization that made it. But knowing the ingredients is not the same as recovering the original method. The ancient Maya did not leave behind a modern laboratory recipe. The exact source of the clay, the preparation of the indigo, the heating temperature, the duration, the mixing ratio, and the ritual context all remain debated. A pigment made in a laboratory can resemble Maya blue, but the question remains whether it carries the same physical behavior, the same texture, the same bond, the same ancient precision. The material was not created by accident alone. It required repeated knowledge, controlled fire, and a tradition that understood how plant color could be locked into stone. What makes Maya blue more haunting is where it appears. This was not merely a decorative color. It was used in sacred spaces, murals, offerings, and ritual objects. At Chichen Itza, blue pigment was connected to ceremonies at the sacred cenote, where offerings and human sacrifices were cast into the water. The color may have symbolized rain, water, sacrifice, renewal, or communication with divine forces. In that context, Maya blue was not just paint. It was a ritual material, a chemical bridge between the human body, the earth, and the gods. Then the knowledge broke. With the arrival of Spanish conquest, Maya cities were disrupted. Priestly traditions were attacked, codices were burned, and entire systems of specialized knowledge were driven underground or destroyed. The people survived, but many technical and ritual lineages were severed. The workshops that once produced Maya blue disappeared. The hands that knew the clay, the dye, and the fire no longer passed the full process forward in visible form. By the time modern science recognized the pigment's brilliance, the living chain behind it had been fractured for centuries. Today, Maya blue can be studied, reproduced in partial ways, and explained through chemistry. Yet the original material still carries something modern replication cannot fully recover: the exact world that made it. It came from local minerals, sacred plants, controlled heat, and ritual purpose. Remove one part, and the material becomes a formula. Keep all parts together, and it becomes a civilization speaking in color. That is why Maya blue feels so unsettling. A people without modern chemical equipment created a pigment stronger than time, then lost the complete cultural machinery that produced it. The jungle swallowed the cities, the books burned, the temples fell silent, but the blue stayed. Tyrian Purple. In the 2nd millennium BCE, along the rocky coasts of the eastern Mediterranean, workers began harvesting small sea snails from tidal pools and shallow waters. To an outsider, the labor would have looked almost meaningless. The shells were tiny, the flesh was foul-smelling, the yield was microscopic, yet from those crushed bodies came one of the most powerful materials in the ancient world. Not a metal, not a weapon, not a stone, a color. The material became known as Tyrian Purple, named after the Phoenician city of Tyre, a maritime power built on trade, secrecy, and the sea. The dye was extracted primarily from murex snails, whose glands contained a colorless or pale fluid that transformed through exposure to light and air. The process was slow, filthy, and brutally inefficient. Thousands of snails could produce only a small amount of dye. Ancient workshops near the coast left behind mountains of broken shells, some rising like artificial hills, evidence of an industry that turned marine life into imperial symbolism. The color itself was unlike ordinary purple. Depending on the species, preparation, and exposure, it could range from deep crimson to dark violet, sometimes appearing almost black in shadow and blazing red under sunlight. More importantly, the dye bonded strongly to fabric. It did not fade easily. It deepened with age. While common colors weakened through washing and exposure, Tyrian purple seemed to grow more dignified over time. A garment dyed with it was not just clothing. It was a portable declaration of wealth, rank, and sacred authority. This is what made the material dangerous. Tyrian purple became associated with kings, emperors, priests, and the elite. In Rome, restrictions were placed on who could wear certain purple garments. A stripe of purple on a toga could mark political rank. A full robe of purple could imply imperial power. The color became law. To wear it without permission was not a fashion mistake. It could be interpreted as a challenge to the structure of the state, but the secret was not merely social. It was technical. Producing the dye required knowing exactly when to remove the gland, how long to expose the liquid to sunlight, how to control fermentation, how to manage heat, salt, and oxygen, and how to apply the dye to wool or linen without ruining the fabric. The smell of the workshops was said to be unbearable, a heavy stench of rotting shellfish and chemical transformation. That smell was the scent of power being manufactured. Ancient sources describe the dye industry, but they do not preserve a complete working formula in modern terms. The makers did not write laboratory manuals. The knowledge lived in coastal workshops, in families, in guild-like traditions, and in the hands of laborers who understood the sea by repetition rather than theory. The process depended on local snail species, seasonal conditions, sunlight, water quality, and timing. Even when modern researchers reproduce versions of the dye, the full ancient production system remains difficult to restore at scale. Then the world changed. Phoenician dominance faded. Roman authority shifted. Trade routes fractured. After the fall of major imperial markets and the rise of cheaper dyes, the brutal economics of Murex purple became harder to sustain. Later, synthetic dyes would make purple accessible to nearly everyone, but that accessibility came at a cost. The original coastal chemistry, the ancient procedure that transformed a living creature into a color reserved for rulers, slipped out of continuous use. The disappearance of Tyrian purple was not just the loss of a dye, it was the collapse of a material hierarchy. For thousands of years, one color separated the common from the divine, the subject from the sovereign, the ordinary body from the body of power. That color came from a tiny gland hidden inside a sea snail, and the people who knew how to unlock it controlled something more potent than decoration. They controlled visibility itself. If Damascus steel made power sharp and Greek fire made power terrifying, Tyrian purple made power visible from across a room. And when the old formula faded, it left behind a strange question. How many symbols of authority were not created by belief alone, but by secret materials no one else knew how to make? Mummification resin. In 1922, when Howard Carter opened the sealed chambers of Tutankhamun's tomb in the Valley of the Kings, the world expected gold. What the cameras could not fully capture was the smell. Beneath the glittering mask, the painted coffins, and the treasures arranged for eternity, there was another material presence inside the tomb. Dark resin, hardened oils, sacred unguents, and blackened embalming compounds that had soaked into linen, wood, and flesh. The body of a dead king had crossed more than 3,000 years of heat, sand, and silence. Something had held the boundary between decay and memory. Egyptian mummification resin was not one material. It was a controlled mixture of substances drawn from plants, minerals, animals, and distant trade routes. Embalmers used conifer resins, pistacia resin, cedar oil, bitumen, beeswax, animal fat, plant oils, and aromatic compounds in carefully chosen combinations. These were not casual perfumes poured over the dead. They were chemical defenses. Some resisted bacteria, some sealed moisture away, some hardened into protective coatings, some masked odor, some may have slowed the destruction of tissue by creating a hostile environment for decay. The appearance of the material was unmistakable. On many mummies, the resin formed a glossy black or dark brown layer, sometimes brittle like old lacquer, sometimes thick and tar like where it had pooled between wrappings. In royal burials, the material could be applied in astonishing quantities, turning linen into armor and coffins into sealed chambers of scent. The resin did not simply preserve the body. The resin transformed the body into an object between worlds, neither alive nor fully surrendered to rot. What makes this material so powerful is the precision behind it. Ancient Egyptian embalmers understood that preservation required sequence. Organs were removed. The body was dried with natron. Oils and resins were applied at specific stages. Linen was layered, sealed, and treated. Amulets were placed between wrappings. Priestly words accompanied physical acts. To modern science, one part looks chemical, another religious. But in the embalming house, the two were inseparable. The resin was both technology and ritual. Modern analysis can identify many ingredients, but the original craft remains incomplete. The same word in an ancient text may refer to different resins depending on period, region, or trade source. A fragrant oil imported through one route may not match the same named substance from another century. The heating temperature, blending order, application method, aging time, and ritual timing were not preserved as a modern manual. The embalmers belonged to specialized traditions. Their knowledge passed through apprenticeship, temple authority, and guarded practice. When the religious system changed, the living formula began to die. The collapse was gradual. Foreign rule altered temple economies. Christianity spread through Egypt. Older funerary practices were discouraged, then abandoned. Workshops closed. Ritual specialists disappeared. Trade routes that once brought rare resins from the Levant, Arabia, and East Africa shifted or fell apart. Tomb robbers stole gold, but time stole something more difficult to replace: the exact chain of knowledge that turned raw substances into a preservation system. There is also a darker pattern in the modern recovery of this material. Tombs were opened, bodies were unwrapped, samples were taken, and fragments were scattered across museums. The resin was treated as evidence, but the world that explained its full meaning had already been broken. Laboratories can detect molecules. They cannot fully reconstruct the decisions of the embalmer standing over a body in a room of heat, incense, linen, and whispered formulas. That is why Egyptian mummification resin belongs among lost ancient materials. Its ingredients can be studied, its effects can be measured, but the complete material was more than chemistry. It was a formula for resisting oblivion, built from oil, smoke, salt, tree sap, and belief. The Egyptians did not defeat death, but for thousands of years they forced death to wait. Egyptian blue. In 1814, during excavations near the ruins of Pompeii, researchers found traces of a brilliant blue color preserved on ancient walls, statues, and decorative fragments. The city had been buried under volcanic ash for nearly 17 centuries, yet the pigment still glowed with a strange intensity. It was not the soft blue of crushed stone. It was sharper, cleaner, and more artificial. Under certain lighting, the color seemed to hold its own quiet radiance, as though the surface had trapped a fragment of the Nile sky and refused to release it. The material was Egyptian blue, one of the earliest known synthetic pigments in human history. Long before modern chemistry, ancient artisans learned to manufacture a blue material from silica, lime, copper compounds, and alkali, heated together until they formed a crystalline substance known today as calcium-copper silicate. The process required temperatures high enough to transform raw minerals into something new, not groundstone, not plant dye, a man-made color born from fire. For ancient Egypt, this was not a minor invention. True blue was difficult to obtain. Lapis lazuli had to be imported from distant regions and was expensive enough to be treated almost like a sacred stone. Egyptian blue offered another path. It allowed artists, priests, and craftsmen to paint the color of water, heaven, divine skin, lotus flowers, protective amulets, and royal decoration without depending entirely on rare imported minerals. The pigment moved from temple walls to tomb chambers, from coffins to statues, from ritual objects to luxury goods. It became part of how Egypt imagined eternity. The appearance of Egyptian blue was unmistakable. In coarse form, the material looked like deep blue granules or small glassy fragments. When ground into powder and mixed with binders, the pigment produced shades ranging from pale sky blue to intense turquoise. Its particles could be blended into paint, pressed into objects, or used as a ceramic-like colorant. It was not just a color sitting on a surface. It was a manufactured material system. Modern science has revealed another strange property. Egyptian blue can emit infrared light when exposed to visible light, a behavior invisible to the human eye but detectable with special imaging equipment. This hidden luminescence has allowed researchers to find traces of the pigment on objects where the visible color has faded almost completely. The ancient makers did not describe infrared emission in scientific language, yet they created a pigment that still communicates through wavelengths the eye cannot see. The unsettling question is not whether Egyptian blue existed. The evidence is everywhere. The question is how its manufacture faded from common use after spreading across Egypt, Greece, and Rome. For centuries, the formula survived. Then, sometime after the Roman period, the large-scale tradition disappeared. Workshops closed, technical lineages broke. Cheaper or different pigments took its place. The exact practical knowledge of how ancient artisans controlled heat, mineral purity, cooling time, grinding texture, and color consistency vanished from living craft. Today, Egyptian blue can be recreated in laboratories, but that does not erase the mystery of its loss. A material once known across the ancient Mediterranean became so forgotten that later generations had to rediscover what it was. The pigment did not vanish because it failed. It vanished because the world that needed it changed, and the specialists who knew how to make it stopped being heard. That is what makes Egyptian blue so haunting. It was born from deliberate chemistry in an age often dismissed as symbolic and primitive. It covered gods, kings, tombs, and sacred walls. Then it slipped into silence, surviving only as dust on broken statues and faint light under modern scanners. The color of eternity was not eternal after all. Only the traces remained. Lycurgus Glass. In 1958, when the British Museum acquired a strange Roman vessel known as the Lycurgus Cup, curators were not simply receiving another luxury object from antiquity. They were receiving a piece of glass that changed color like a trap signal. Under reflected light, the cup appeared jade green. When light passed through the glass from behind, the same vessel turned a deep, glowing red, almost like wine illuminated from within. The transformation was so dramatic that it seemed less like decoration and more like a material designed to deceive the eye. The cup itself was created in the 4th century CE and stands roughly 6 inches tall. Its outer surface is carved into a cage-like scene, showing King Lycurgus of Thrace entangled in vines, a mythological punishment rendered in extraordinary detail. The figures are not merely painted on the glass. They are cut from the same body of material, leaving a delicate outer web connected to the inner cup by tiny glass bridges. Even without the color change, the object would be a masterpiece. With the color change, it becomes something far stranger. The material is known as dichroic glass, meaning it shows different colors depending on how light interacts with it. Modern analysis revealed that the glass contains incredibly small particles of gold and silver dispersed through the material. These particles, measured at the scale of billionths of a meter, interact with light in ways that alter the wavelengths scattered and transmitted. In simple terms, the glass behaves like a controlled optical filter. But the unsettling part is the date. Roman artisans created this effect more than 1,500 years before modern nanotechnology gave scientists the language to describe what was happening. This does not mean the Romans had nanotechnology in the modern industrial sense, but it does mean they produced a material whose behavior depends on particles so small that no ancient craftsman could have seen them directly. The question becomes sharper from there. Was the effect deliberate, or was the cup a miraculous accident? If accidental, why does the result seem so visually perfect for an elite ritual vessel? If deliberate, how did Roman glassmakers learn to control metal particles inside molten glass with such precision? Glassmaking in the Roman world was already sophisticated. Artisans understood colorants, furnace conditions, blowing, casting, cutting, and polishing. They used copper, manganese, cobalt, iron, and other materials to create vivid effects. But dichroic glass required a delicate balance. Too much metal, and the glass could become dark or opaque. Too little, and the color shift would vanish. Heat the mixture incorrectly, and the particles would not form in the right way. The Lycurgus cup suggests not just skill, but a dangerous closeness to a process that later centuries failed to preserve. The chain of knowledge disappeared. No known Roman manual explains exactly how to make this kind of glass. No surviving workshop tradition carried the technique into the medieval world in a continuous, recognizable form. The cup remained as a silent witness, admired for its beauty long before its microscopic secret was understood. Only with modern instruments could researchers detect the gold and silver particles responsible for the transformation. That is what makes the material so haunting. A Roman artisan may have learned, through experiment or guarded workshop practice, how to suspend precious metals inside glass so finely that light itself changed behavior. Then that knowledge slipped away, not destroyed in a single fire, not banned by imperial decree, lost more quietly, through the collapse of luxury markets, changing tastes, broken supply lines, and dead workshops, whose methods were never written for outsiders. Today, modern science can reproduce dichroic glass using controlled processes. But the ancient method that produced the Lycurgus cup remains uncertain. The object survives. The exact hands, temperatures, furnace atmosphere, metal preparation, and sequence of work do not. The cup still changes color. That is the most unsettling part. The material continues performing its secret in plain sight, centuries after the people who knew how to command that secret vanished. It is not just a Roman masterpiece. It is a message from a lost furnace written in green and red light. Ulfberht Steel. In 1932, inside a corroded Viking grave in northern Europe, archaeologists lifted a sword from the soil and found a name still visible across the blade. The letters were strange, almost ceremonial, inlaid into the iron like a signature from a vanished forge. They read plus VLFBERH+T. At first, it seemed like a maker's mark. Then more swords appeared across Europe bearing the same inscription. Some were crude copies. Others were something far more disturbing. Their steel was too clean, too advanced, and too far ahead of the world that supposedly made them. The Ulfberht swords date roughly from the 9th to the 11th centuries, a period often imagined through raids, wooden ships, chainmail, and brutal close combat. Most European blades of that age were made from bloomery iron filled with slag and impurities. They could be effective, but inconsistent. Many bent, some cracked. Their quality depended heavily on the skill of the smith and the limitations of the furnace. But certain Ulfberht blades were different. When examined by modern metallurgists, some showed unusually high carbon content and remarkably low slag. This was not ordinary Viking Age iron. This was closer to crucible steel. That detail changes everything. Crucible steel requires iron and carbon to be heated inside a sealed container at temperatures high enough to melt and homogenize the metal. The result can be far cleaner and stronger than typical bloomery steel, but such temperatures were difficult to achieve in northern European furnaces of the time. The technology was more closely associated with regions far to the east, including Central Asia, Persia, and India. If the finest Ulfberht blades truly used crucible steel, then the material either traveled thousands of miles through trade networks, or a small number of European smiths possessed access to a technique most of their continent did not understand. The physical sword made the mystery visible. A true high-quality Ulfberht blade could be flexible, strong, and sharp enough to survive combat without the flaws common in inferior steel. The inscription itself may have functioned like a brand, a sacred name, or a mark of elite manufacture. Warriors who carried such swords did not merely own weapons. They owned rare material science shaped into status and violence. On a battlefield, where a snapped blade could mean death within seconds, the difference between poor iron and clean steel was not cosmetic. It was survival. Then came the copies. Some Ulfberht swords with similar inscriptions were made from lower quality metal, suggesting imitation. That means the original blades were famous enough to be counterfeited. A name once attached to advanced steel became a symbol others tried to reproduce without possessing the same material. This is one of the clearest signs that the real formula was restricted. People knew the legend. They did not all know the method. The question is where that method went. If the crucible steel came from Eastern trade, then the Ulfberht blades were dependent on long-distance routes linking the Viking world to the Islamic world and beyond. Silver, slaves, furs, and weapons moved through river systems and trading towns. When those routes changed, the material supply may have vanished. If the knowledge existed in a small workshop tradition, then the death of a few smiths or the destruction of a few furnaces could have erased the chain forever. No complete manual survives explaining how the original Ulfberht blades were made. No known workshop has been identified as the uncontested source. The swords remain scattered across museums and collections, their inscriptions still glowing faintly under corrosion, their steel still asking questions the grave never answered. What makes the Ulfberht material so unsettling is not just that it was advanced. It is that it appeared in the hands of warriors who lived centuries before Europe's later metallurgical revolution. Somewhere, someone knew how to obtain or create steel that most of the continent could not match. Then that knowledge slipped behind trade, secrecy, imitation, and death. The blades survived. The forge did not. Egyptian Faience. In 1898, during excavations in the ancient cemeteries of Abydos, archaeologists uncovered thousands of small blue-green objects buried with the dead. Beads, amulets, scarabs, tiles, figurines, and ritual vessels emerged from the sand with a color that seemed too bright for their age. Some were cracked, some were worn, some had slept under desert pressure for more than 3,000 years. Yet the surfaces still carried a luminous glaze, a strange turquoise shine that looked less like pottery and more like frozen water from another world. The material was Egyptian faience. Despite the name, it was not true faience in the later European sense. It was not ordinary clay pottery. It was a silica-based material made from crushed quartz or sand, mixed with small amounts of lime, alkali, and copper compounds. When fired, the surface developed a glassy blue-green coating. The result looked like a stone, a ceramic, and a glaze at the same time, but belonged fully to none of them. It was a manufactured material designed to imitate the colors of rare minerals such as turquoise and lapis lazuli, while carrying its own ritual identity. Egyptian faience was everywhere in the ancient Egyptian world. It appeared on protective amulets placed over the heart, on beads wrapped into mummy linen, on tiles lining sacred chambers, and on figurines associated with rebirth. The blue-green color mattered deeply. It suggested water, vegetation, regeneration, the Nile flood, and the life force returning after death. To modernize, faience may look decorative. To the Egyptians, it was a material of transformation. It was earth and mineral changed by fire into a surface that looked alive. The method was deceptively complex. Ancient craftsmen could create the glaze in several ways. In one method, soluble salts inside the object migrated outward during drying and formed a glaze on the surface during firing. In another, a slurry glaze was applied externally. In a third, objects were buried in glazing powder inside the kiln, allowing the surface to react during heating. Each method required control of moisture, grain size, copper content, alkali concentration, firing temperature, and kiln atmosphere. Too little heat, and the surface remained dull. Too much heat, and the shape could deform. Too much copper, and the color darkened. Too little, and the sacred blue faded toward lifeless gray. Modern laboratories can reproduce Egyptian faience in broad terms, but recreating the exact appearance, texture, surface depth, and workshop consistency of ancient examples remains difficult. Some original pieces have a soft glow that comes from uneven glaze thickness and mineral migration, not from a simple coating. Others show tiny bubbles, crystalline zones, and surface patterns that reveal a firing environment controlled through experience rather than instruments. The ancient maker did not read a digital thermometer. The ancient maker read the furnace color, the smell of heat, the dryness of the body, and the behavior of the glaze as though the material were speaking. Then the tradition changed. Egyptian religious life transformed under foreign rule, Hellenistic influence, Roman control, and later Christianization. Temple economies weakened, funerary industries shifted. The demand for faience amulets and sacred blue-green objects declined. Workshops that once supplied priests, embalmers, tomb builders, and households lost their purpose. The material did not disappear overnight. It faded with the world that gave it meaning. That is the true loss. The ingredients are not entirely unknown. The chemistry is not beyond modern science. But Egyptian faience was more than a silica mixture with copper glaze. It was a material language. Every blue scarab, every glazed bead, every small figure placed beside the dead carried the same message. Decay was not the end, and matter could be reborn through fire. When that belief system fractured, the formula survived only as fragments. Museums kept the objects. Laboratories studied the glaze, but the living chain between mineral, kiln, priest, artisan, and tomb was broken. Egyptian faience was not made to imitate beauty. It was made to manufacture eternity in blue-green light. Goujian Sword. In 1965, inside a waterlogged tomb in Hubei Province, China, archaeologists opened a sealed wooden coffin and found a sword resting beside a long, dead nobleman. The tomb had been buried for more than 2,000 years. Groundwater had entered the chamber. Organic materials had softened. Wood had darkened. Time had done what time always does. Then the sword was drawn from its lacquered scabbard. The blade still shone. It was not a massive weapon. The Sword of Goujian measured a little under 22 inches long, elegant rather than brutal, with a narrow bronze body and a hilt bound for control. Across the blade ran a repeating dark diamond pattern, precise and hypnotic, like scales on a ceremonial serpent. Near the guard, an inscription identified the owner, Goujian, King of Yue, one of the most famous rulers of China's spring and autumn period. The weapon had not emerged as a corroded lump of ancient metal. It looked disturbingly intact, as if the tomb had not been a grave, but a vault. When specialists examined the sword, the mystery deepened. Bronze normally corrodes. Buried bronze can develop green patina, mineral crust, pitting, and structural weakness. Yet this blade retained a remarkable surface condition and a sharp edge. Reports from the time claimed the sword could still cut paper. Whether exaggerated or not, the physical fact remained unsettling. A weapon sealed in a damp tomb for more than 2 millennia had survived with an integrity that seemed far beyond expectation. The material was not ordinary bronze. Analysis showed a carefully controlled copper-tin alloy with different compositional zones across the blade. The central spine contained a structure suited for resilience, while the edges contained higher tin content, making them harder and better able to hold sharpness. This was not random casting. It suggested a sophisticated understanding of how to balance strength and cutting performance within a single weapon. The sword was engineered so that different parts of the same blade performed different roles. Its surface added another layer of complexity. The famous diamond pattern was not mere ornament. The dark geometric texture may have resulted from surface treatment, casting technique, chemical interaction, or controlled finishing methods that remain debated. The scabbard and tomb conditions also played a role in preservation. The sword had been sealed tightly inside lacquered protection, reducing exposure to oxygen. But preservation alone does not explain the precision of the alloy, the blade geometry, and the symbolic perfection of the object. This was both weapon and royal statement. For the ancient Yue state, sword-making was not simply metalwork. It was a strategic art. The region was famous for blades, warfare, and metallurgical skill. Legends described master swordsmiths whose creations carried names, spirits, and destinies. Behind the legends was real technology: mining, smelting, casting, grinding, polishing, inlaying, and heat control. The Sword of Goujian represents a moment when royal power, battlefield utility, and material science converged in bronze. Then the world changed. Iron and steel rose. Bronze sword traditions declined. States fell. Workshops disappeared. The specialized knowledge of Yue sword-making was absorbed, forgotten, or transformed beyond recognition. Later generations remembered the kings and battles, but the exact workshop procedures that produced blades like Goujian's sword did not survive as a complete living tradition. The sword remained. The system that made the sword vanished. Modern metallurgy can explain much of the object. It can measure the alloy. It can model the hardness. It can identify preservation factors. But explanation is not the same as recovery. The ancient makers did not work from modern equations. They achieved control through furnace practice, inherited craft, and repeated experimentation over generations. Their knowledge lived in hands, not textbooks. That is why the Sword of Goujian belongs at the end of this archive. Unlike Roman flexible glass, the sword is not a rumor. Unlike Greek fire, the sword is not only a text. Unlike Damascus Steel, the sword is not known only through scattered blades and lost routes. The Sword of Goujian is still here. It can be seen. It can be measured, it can be admired, and still it refuses to give back everything it knows. A king died, a kingdom vanished, a tomb filled with water, but the bronze remembered. Conclusion: these lost ancient materials reveal a disturbing pattern. Across continents and centuries, ancient people created substances that did more than serve daily life. They cut through armor, burned across water, preserved the dead, colored sacred walls, changed under light, resisted corrosion, and endured salt, soil, and time with a resilience that still unsettles modern science. The mystery is not simply that these materials existed. The deeper mystery is how their knowledge disappeared. Some vanished when trade routes collapsed. Some died with priesthoods, guilds, and royal workshops. Some were guarded so tightly that secrecy became a tomb. Others survived as objects in museums, while the living chain of hands, furnaces, minerals, temperatures, rituals, and timing was broken beyond repair. What remains is a strange contradiction. Modern laboratories can analyze fragments, identify compounds, and simulate ancient recipes. Yet many of these materials still resist full recovery because the original formula was never just chemistry. It was geography. It was apprenticeship. It was belief. It was local ore, sacred clay, coastal snails, volcanic ash, sealed tombs, and craftsmen who understood matter through generations of trial, failure, and silence. Every lost material is a warning. Progress is not guaranteed to move forward in a straight line. Knowledge can vanish. A single destroyed workshop, a burned manuscript, a dead master, or a broken trade route can erase a technology for thousands of years. The question is not whether ancient civilizations were more advanced than we imagined. The question is how much of their knowledge is still lying in plain sight, waiting inside rustless blades, blue pigments, black resins, and stones that refuse to decay. History may not have forgotten these materials. Perhaps history was never allowed to remember them completely.